Applications of the PN junction diode. First of all, we have the light emitting diode, where we have a diode with a junction near the surface of the material, where we have a clear cover, and we are very familiar with this circuit symbol. We've seen that in a forward bias PN junction diode, holes and electrons pass through the junction in opposite directions. Now, as that happens, sometimes the holes and the electrons will meet and recombine. And when this happens, energy is emitted in the form of a photon. That happens in the LED. In a regular diode, it would be emitted as another form of radiation, for example, heat. For each recombination of electron and holes, one photon of radiation is emitted. In most semiconductors, this takes the form of heat, as I said, resulting in a temperature rise. However, in some materials, the energy is emitted as light. The only difference between heat radiation and light radiation is the frequency of the photons. And the frequency of the photons is determined by the energy. The energy is the gap, the potential barrier that has been overcome in order for the electrons and the holes to recombine. So we call this a light emitting diode. In the junction, whilst the diode is forward biased, positive and negative charge carriers, that is holes and electrons, may combine to give a quantum of radiation, that is a photon of radiation. So the photodiode is basically an LED in reverse. In the LED, the electrons and the holes recombine to release photons of light. In the photodiode, light incident on the junction takes a combined hole and electron and separates it. So that means positive and negative charges are produced by the action of light on the PN junction. So when light falls on a junction, electron-hole pairs are produced. Each photon gives up its energy and produces one electron-hole pair. The electron-hole pair then move in opposite directions because they have opposite charges, and a small voltage is produced across the diode. So we can see in the diagram here, a photon is incident on the junction and an electron-hole pair is generated. The hole obviously is attracted towards the n-type material and the electron towards the p-type. If the irradiance increases, that is, if the number of photons increases, more electron-hole pairs are produced and consequently more voltage across the photodiode. Because the photodiode produces these electron-hole pairs, it can be used in two different modes. First of all, the photovoltaic mode. In this mode, there's no bias voltage involved. There's no potential being provided. The photons are incident on the junction. They have their energy absorbed, freeing electrons and creating electron-hole pairs. As this is done, a voltage is generated by the separation of the electron and hole. More intense light, that is more photons incident on the surface per second, will lead to more electron-hole pairs being produced and therefore a higher voltage. In fact, the voltage is proportional to the light irradiance. So we can think of this photodiode acting in photovoltaic mode being a solar cell. In a solar cell, the greater amount of light incident on it, the more electrical energy is produced. When light shines on the photodiode, the motor spins round. The greater the amount of irradiance, the faster the motor spins. And that's because more light, more electron-hole pairs are generated, more movement of electrons, more current, the motor moves faster. In the photovoltaic mode, a photodiode may be used to supply power to a load, or, for example, to this motor. The other one is photoconductive mode. Now, in photoconductive mode, we connect the photodiode in reverse bias. So it's connected to the supply, but it's reverse biased, so that means it wouldn't ordinarily conduct. If it's kept in the dark, it acts like an ordinary reverse bias PN junction, doesn't conduct, no current can get through. However, if a small amount of light is shining on the junction, it will generate electron-hole pairs. This will provide a number of charges in the depletion layer, which decreases the resistance and enables current to flow. More light, more photons per second, means more electron hole pairs generated per second, more free charge carriers, and therefore less resistance. So the photodiode acts as a light-dependent resistor. That is, as the light level increases, the resistance decreases. In the photoconductive mode, the photodiode may be used as a light sensor, because the more light that goes in, the more conduction happens. So we see in the diagram here, light is incident on a junction. The depletion layer is quite big, because remember this is reverse biased. And when that light is incident on the junction, we have an electron hole pair generated within the depletion layer. The electron hole pair will then move across to the individual materials, the p-type and the n-type, thus generating a current. If we look at it in terms of band theory, we have our depletion region here with our p-n junction. We have majority positive charge carriers within the valence band of the p-type, majority negative charge carriers, that is electrons within the conduction band of the n-type. And at the junction, we can have the negative and the positive coming together. So if we're forward biased, we release photons of light. If we are reverse biased, we can allow conduction to happen. So we need to take note here. The switching action on a reverse bias diode is really, really fast. So that means that the electron hole pairs created in the photodiode recombine very rapidly. Light goes onto the photodiode, electron hole pairs are generated. If there isn't light there, then those electron hole pairs will recombine. Because of this, we can say that a photodiode can be very, very useful in detecting rapid changes in light level. So, for example, if I was measuring the speed of something moving very, very fast, I could use the reverse bias diode for a light gate, or in fiber optic communication, where we have rapid changes in light level, which effectively represent rapid changes in electrical energy. Those rapid changes are zeros and ones. That's data transfer. We need that to be quite quick. When we have a diode operating in reverse bias, remember there's that leakage current which occurs, but the leakage current is not really affected by the amount of potential that's provided for the reverse bias. So we have a supply and that has a potential, and that's what's causing the reverse bias. But as long as that potential is below the breakdown voltage, the current is pretty much constant, as in the leakage current is pretty much constant all the way through. So any changes to that current, we can say are proportional, almost directly proportional to the light level as opposed to anything else. So it can be very, very accurate in determining what changes occurred within the light level. So a summary of the semiconductor devices. We've got p-n junction diode. It can be forward biased or reverse biased. Forward bias is where the n-type material is connected to the negative terminal, and that will allow for conduction. A reverse bias is where the n-type material is connected to the positive terminal and therefore it doesn't conduct. The light emitting diode, if it's forward biased, it conducts and light is emitted as the electron holes combine. In reverse bias, it does not conduct, so no light can be emitted. For the photodiode, if there's no bias acting on it, then it acts in photovoltaic mode, acts like a solar cell. The light energy incident on the photodiode then goes produce an electrical potential. In reverse bias, it acts in photoconductive mode. So normally when a diode's in reverse bias, it doesn't conduct, but if we have light incident on it, we can decrease its resistance and we can allow conduction to happen. So that's like our LDR.